says grain is shipped to the mills in railway cars, and each car is able to hold 1 ton of wheat. But I don't see how this has come into play in the question here, like in the answer.
Okay, which one? Each car is. What would you want to see? Which specific phrase?
Like, it's to hold 1 ton of wheat. So in a normal circumstance, if this was to be an exam question, I would think maybe it's to be part of the question, like a limitation or something. Or you're just to eliminate it.
Oh, the thing is that you are told that each car, remember, you have to know what railroad cars are. If you don't know what railroad cars are, when you see a train going, you know that train is kind of divided into parts, boxes.
Yes, sir.
When that train is not carrying human beings, it is carrying something that looks like boxes, and the items are in it. These boxes, these divisions are called railroad cars. And when each car will have 1 ton of wheat, but then there is a bigger region of the car. So each car will have 1 ton, each car will have 1 ton, each car will have 1 ton. Now, when you look at St. Louis, Kansas City is supposed to supply 150. So you will see that these 1 ton, 150 of them. In fact, I have seen it a lot in the UK, all over, Manchester, they are carrying these things. You see that there are so many of them. They keep coming. They keep going and going and going and going. So many. That compartmentalization, that divisions, okay, is what this one is talking about. So the 1 ton doesn't mean anything. It simply means 1 box. And there are multiple of these boxes.
Okay. Okay, so it has no effect in.
It has no effect at all. The key point is the number of the tons.
All right, sure. Thank you, sir.
All right, so once you have this, the next thing you want to do is to formulate the model. And this is a minimization model. Minimization will mean that, and I said you should use the graph to guide you. So this is a graph. So watch the graph. If I want to minimize, this is what you do. You write your Z min, watch it, equal to, who can tell me the first thing that must come and why? Who can tell me the first thing that you must write for the objective function? Okay, Hannison. Hannison. Solomon.
Okay, let me.
The decision variables.
Yeah, so what will you write? That's what I'm asking.
Okay, so I would write X14 or 1A.
Yeah, let's maintain your 4.
Okay. But then we have the cost of that decision variable, which would be the 6. So it would be 6x14.
Very good. So the first thing you do is write 6x14. Continue. So, by the way, what he has done is that he has dealt with this line. That's what he has just done. Continue. I want to know which one you are going to bring first. Next.
8x15.
Good. That is what should be. Okay. So it should be plus 8x15. Which is the next?
Plus 10x16.
Very good. Plus 10x16. Continue. Let me see.
Plus 2. Sorry, no, not 2. Sorry. Plus 7x25. 24. Sorry. 7x24.
Very good. 7x24.
Plus 11x25.
11x25. Guys, watch what we are doing. Continue.
Plus 11x26.
Plus 11x26. Continue.
Plus 4x3. 4.
4x3, 4. Continue.
5x3, 5.
Very good. And the lastly?
12x3, 6.
Ladies and gentlemen, this is how your objective function is supposed to be. So you can see that the decision variables are in 2-digit numbers. Okay, they're in 2 different numbers, not x2, x3, but x2 something. And now you understand what is happening. This is how you formulate it. Done. Finish. Who is not clear? Who's not clear? Okay. So what you do now is that once you have written your objective function, you now go to the constraint. Who can tell me how many constraints are here? Who can tell me how many constraints are here? How many constraints are here? Let me see. 6. Very good. Because there are 6 circles, 6 nodes. So there are 6 constraints. So this is how you do it. You write the supply constraint first, and then you write the demand constraint second. So what is the supply constraint? The first one is 1 here. The second is 2 here. The third is 3 here. Now watch how you write it. If you follow this approach, you will always do it well. You have to check how many acts are leaving that constraint. So take the first one, number 1, node 1. How many acts are leaving number 1? How many acts?
3.
Good. And because they are leaving, please pay attention, because they are leaving, we can choose to write the answers to be minus.
Sir, please, I have a question.
Right.
Yes, we said we have 6 constraints, but from our previous lesson, we needed to add the non-negativity constraint. So I wanted to ask if
it's not part. It's not part. Okay.
Okay.
From linear programming, we said that non-negativity is always not part of the main constraint.
Okay, thank you.
So because node 1 is a supply node, and supply means that something is leaving it, we use minus to indicate that the thing is leaving. We use plus to indicate that the thing is entering, or the thing is receiving. So because these acts, the blue acts here, are leaving number 1, the constraint for that number 1 would be, and I'm doing the first one.
We are debit and credit.
Okay, so I think I have to mute everybody. Then when you have a question, you can ask, because otherwise it's not going to help. You can raise your hand, then I can call. Okay, so because they are leaving, you have to bring the minus. So look at the number 1 here. What is leaving? X1A is leaving, but we call it X14. So your first constraint is going to be minus X14. The next thing leaving is X15. This one here, X15. So you write minus X15. The next one that is leaving it is X16. So you write minus X16. Then you make it equal to. Now, why are we doing equal to? And here's the thing. Check the total supply and check the total demand. They were both 600, 600. Therefore, everything we are going to have is going to be what? Equal to. And that is why we write equal to. Equal to what? For the constraint 1 is equal to the 150. So these are the things that are leaving the node 1. So you write equal to negative 150. The negative sign is simply implying leaving. In fact, when I apply positive to all of them, they will all become positive. When I apply another negative, they all become positive. So that is why you write the constraint 1. That is how you document the constraint 1. Any question on the constraint 1? So you can see this constraint. I will be happy if one of you is able to give me the next constraint. You can walk me through constraint number 2. How should we write it? Constraint number 2. This one. Who can tell me how we will formulate constraint number 2? So if you can walk me through this, you are good. Let me go to Sefacon.
All right.
Yes, Sefacon.
All right. Constraint number 2 will be because
Oh, don't give me the because,
RBI,
just write your answer straight.
okay, negative x24.
Okay, so
Negative.
wait. Once you bring the number, if you can check, I did not add the cost.
Yes, please.
When you are writing the constraint, you only bring the cost when you are writing the objective function.
Yes, please.
So start.
Okay. Minus x24 minus x25 and minus x26 equal to 175.
Equal to
175. Please.
That would have been wrong because they are leaving. It should be equal to minus 175.
Very well. Thank you.
Okay. Now, so I'm assuming that we have done this. Let's ignore this one. Who can give me the last constraint here? This one is on the demand side, not the supply, but demand. The last constraint here, number 6. Who can give me that one? Yes, number 6. Who can give me that last constraint? Remember that one is a demand node, not a supply node. A demand node. Foster. Let me see whether you can be able to do something. Yes, Foster.
Okay, so it's going to be x16 plus x26.
Once I'm writing x16
plus x26
x26
plus x36
x36
is equal to 300.
Equal to 300. That is perfect. Why didn't you add the minuses?
Because it's the demand, so they are adding, it's coming from the supply to the demand, so it's being added.
The word you are looking for is because it is receiving.
Yes, it's receiving.
It's not sending, it's receiving. So that is a positive thing. It's not leaving it, it's entering it. So when it's entering it, it's adding to you. Very good. Okay. And it is still equal to, because we have already confirmed that the whole thing is a balanced transportation model, which means everything will be equal to. So you're supposed to have 6 of these constraints, all of it like that. Yes, Solomon, you have a question? I'm supposed to have
Yes, a question.
Yeah.
Even though we've understood that it's a balanced model, realistically, isn't it possible that you may supply, or no, not supply, the destination may receive less than the 300, even though it's supposed to receive?
So your simple question is that couldn't we have unbalanced model?
Couldn't we, instead of saying equal to, say less than or equal to?
Yeah, and I'm saying that you are asking, couldn't we also have unbalanced? Is that not your question?
Yes, that's my question.
You are coming to that one right now.
Okay, thank you.
Yeah, you can have a situation where everything is not balanced, but sometimes you have an unbalanced transportation model. So, but for now, this is a balance. So if you are to do this well, and I hope you were all doing it. If you are doing it, this is your model that you're going to have. Everything that we've done so far, this is it. And the last thing you will have is your non-negativity constraint. I want to show you something here. Coming back to the question that you asked. So look at this. That you always check the total before you determine whether it's balanced or unbalanced. Now, if demand was more than supply, that was his question. Suppose that one of the items, Cincinnati was the last one, the last node 6. Suppose it was not 300 there, but it was rather not 300, but it was rather 350. what happens to the total? If that is the case, you see that the total supply will still be 600, but the total demand will be 650. That's what it means. Now, because the total demand is 650, all the constraints, all the three constraints at the total demand must have less than or equal to sign. And I want to repeat this, because if you don't take it, you will miss this one. Because the total demand is 650, when you're writing the three constraints for the supply, they will still maintain their equal to, but when you're writing the three constraints for the demand, all three of them will have less than or equal to. What if the total supply was rather 650? Well, the opposite. If the total supply was rather 650, then all the constraints for the supply, each one will have the less than or equal to, and then the demand will maintain the equality. I hope you get this. If you don't get this, you can raise your hand and I'll explain further. So this is how it's going to be. If, Rebecca, you seem to have a question, so you can ask your question before we proceed.
Sir,
Yeah.
Doug, please, could you please explain it once more, that if it is, this one were to the 650 and this one were to the 600, you said it should be less or equal to. Could you please explain that one once more for me, please?
Sure. So if total demand, so this is TD, total supply, okay? TS is total supply, and TD is total demand. Already we know that they were all 600. Okay? So here was 600, and then here was 600. And so all of these things became equal to. Now, we have a situation where this one is still 600, but this one, the total is 650. The one whose total is more, and in this case, total demand, they will have the less than or equal to symbol, whilst the other maintains the equality. So these ones are the total supply. They will maintain their equality. But this one, the total demand, which was the more, that will rather have less than or equal to sign. And why is that so? Come on, you want to think about it, you will understand the intuition behind. The intuition is that there are some items that are going to Chicago, this first one. There are some items that are going to St. Louis. There are some items that are going to Cincinnati. All of these are more. The total is more than what is being supplied. So it means that whatever is coming here, relatively speaking, it is going to be less, whatever is coming. Because the total here, they are demanding more. But the total of what they are demanding is more than the total of what is being supplied. So what it means that whatever, I don't know what the items are coming here, all right, but whatever it is going to be less or equal to. Now let's say this one is equal to, let's say, I don't know which one, but let's say this one is equal to. And let's say the second one is equal to. Then I will expect this one to be less than, and I'm talking about the things on the left. So if the things on the left-hand side here is equal to then what it means is that for this one, we have 200 equal to 200, all right? And this second one, if it is equal to, we have 200 is equal to 200. But according to the rule, the total is more than the total here. So I'm expecting that for this right-hand side here to be 650, then whatever is coming here must be less than what is on the right-hand side. Okay, it must be, because already we know that this total here is 650 and this total here. So I know that whatever is coming here, if it is 200, oh, sorry, this one was 100. So whatever is coming here must be less. So in order not to know which one is less and which one is not less, you just say that all of them must be equal to or less than or equal to, because one of them will satisfy that constraint we are looking for. Rebecca, I hope you understand. Okay, so that is how you are able to handle it. But that's intuition. So the rule is that the one that is always having more, the bigger, should have the what? The less than or equal to some. That's the rule. That's basically it. So you formulated this. Once you've done all the formulation nicely as we have done here. Okay. Once you've done everything nicely here. Oh, by the way, remember that the first ones, I told you that it is minus, but you can remove all the minuses, as you can see I did here. You can remove all the minuses here and they will all become what? Plus. So you can remove the minuses here, the minuses here, the minuses there, the minuses there, and then they all become plus because they were all minuses. That is why you can see that the last parts here, I've made all of them plus, plus, plus. And don't forget your non-negativity constraint. You can see that Xij is greater or equal to 0. And your decision variables must be well defined. I, J. What is a I? What is a J? So in our case here, if you are defining, the I is going to be 1, 2, and 3. The J is going to be 4, 5, and 6. That is how it's going to. And once you've done all the definitions nicely, you are now formulated the model. Finished. You will have to solve the model, but I will not bore you in solving the model in an exam situation, just like the integer program. Rather, I will solve the model. Okay. UT has a question.
Please, sir.
Yeah.
In writing the decision, the constraints for the first time, that you will have to add the negative. How do you remove the negative and turn it to become positive? Will you write the negative first before coming to write the positive one?
You can choose not to even change them to positive, and you can choose to write a positive straight away.
Okay.
Either one is
fine.
Thank you. Okay.
Thank you.
So once, is there another question somebody has? Let me go to Dorothy. Dorothy, you have a question? Yes, Dorothy.
Stop me on mute.
Yeah, Dorothy, go ahead. We can hear you.
Okay, please, sorry. For the unbalanced equation, could there be a point where supply is rather more than the demand side?
Yes, and I gave that example. If supply is more than the demand, then the supply will have the less than or equal to. Okay, so sometimes when you ask questions, it would be nice to keep your muting on, or muting on, so that when I finish, you can confirm that you understand before you mute yourself. All right, so now that we've been able to formulate this, we can now go ahead and then we can solve the problem using Excel. That's for later. Do that later. But for now, there are some few things I want you to note about transportation problem. There's a route called prohibited route in transportation problem, and I want you to understand it. There's always a question on this. So it's, as the name sounds, when I am prohibiting you from doing something, it means I'm not allowing you to use the thing. A prohibited route is a route where it's not possible to use. If it is transportation, you cannot pass through that road if it is a road. If it is a railway line, you cannot use that railway line. So sometimes in London Underground, they will tell you that the Piccadilly line is closed. So you can't use the Piccadilly line. You can't use the black line, the northern line. You can't use the blue line. You can't use the red line, the central line. You can't use any. So the reason is because something is going on there. There is a road construction. There is a bad road condition. There is a strike action. There is some unexpected flood. making it very difficult to use that road. And as a modeler, you got to incorporate such uncertainties or such certainties into the model. How do you capture that into your model? This is what you do. You can give the cost of that, because you see, if the road is blocked and you want to pass that road, it means you're going to incur some huge costs, as huge as maybe death. Like if it is a bridge and you have a dead end of the road, and you still want to use that dead end, you die. So the way to do that is to assign a huge cost to that route. Let's assume that that prohibited route is X17. You will give it a large cost, say 100 or 1,000 or million, whatever it is. And when you give it that huge cost value, it makes it a prohibited route. It means that nobody should use that route. That is how you handle it. That is how you bring it into the model. So if you are told that, but the route, so suppose when I was giving you these write-ups, okay, suppose when I was giving you the drawings, and I had said that, let me see if I can show you that. If I had given you something like, I need to use a graph for it to make beautiful sense. Suppose I had told you that this route here, the route from 3 to 6, suppose I told you that the route from 3 to 6 here is a prohibited route. And I did not give you the 12 number, the number 12. What you will do is that you will write X, 3, 6, and give it a huge value cost of, say, 100. And you'll bring that into the model to indicate that you understand that that is what? A prohibited route. I hope you get it. Or you give it even 1,000 to indicate that that is a prohibited route. So in your model, which model? In your objective function, I will expect to see this there. What about in the constraint? In the constraint, it is still going to be, whatever you expected it to be, it's still going to be that. So in the constraint, if it is less than or whatever, it's still going to be what it is. Yes, Isaac, you have a question.
Yes, Doc, please. So the figure that you put in front of the X36, is it arbitrary? Can you choose any number, or there is a range?
No, you can choose any number, but it should be bigger than most of the numbers that you have, way bigger.
Okay.
Yeah. So if you look at the numbers I'm having here, the numbers are between.
It should not be.
It should not be what? You don't know what it should not be here. Anyway, so that's a prohibited route. Sure, I'm sure you got a picture. Okay. I want to talk about prohibited routes. That is it. So prohibited, give it a huge number. Give it 1,000. That's all. Give it some 1,000, and then you are sorted. So that is all you do. Okay. Princess, you have a question. Yeah, Princess.
Hello, sir. Yes, please, I want you to come again with the reduced cost. With the one I said, the prohibited, like the prohibited routes. I didn't really get it. You can please.
So when you have a route, when you are told that the route from Des Moines, the route from Des Moines is Des Moines to Cincinnati is a prohibited route. So this is what you are told in the story. You will notice that they will not tell you the cost for that route. In this case, the cost is 12, but you will notice that they will not give you the cost. Once you are not given the cost, because you've been told that it's a prohibited route, you will assign a huge cost to it in the objective function. Remember, in the objective function alone. Or the next option, by the way, guys, let me give you the easier option. The easier option is that you don't even include that route in your model. Exclude it from the entire model. So when you are writing the objective function, that x36 will not even be included at all. Okay? So if you look at this objective function, that one here, this one will not be included at all. You exclude it, meaning that it's what? It's a prohibited route. But if you're going to include it, you must give it a huge cost, way above. So if the costs are 2 digits, you give it a huge cost of 3 digits or 4 digits numbers. That's what I'm talking about. Now, so that is how, yes, Princess.
Thank you.
Yeah,
Thank
Kofi.
you.
Yes,
Okay.
look, in the same situation, this is a minimization, so giving it a huge cost makes it, and a maximization, are you going to negate that value even if you make it a huge cost, or is it going to be
Yes, you're going to negate it. So you're going to give it a negative value, okay, whilst the others are positive. And a negative value in that same digit operation. So if you were giving a positive 1,000, it would be a negative 1,000.
Okay.
Or like I said before, you exclude it completely. Okay, Hansen, you have a question? Yeah, Mark. All right, I think Mark's situation is handled.
Hello.
Yes.
Can I hear? Yes, sir, my question is, so supposing we are to include it, what will be the impact on the constraints? I will have no impact on the constraints.
No, so you just write a constraint as it is.
Okay, thank you, sir.
All right, so that is a transportation model. Now let's go to a transshipment model. Okay. A transshipment model. Okay. How this very transportation model works, I've solved it in the Excel. Look at it, and then you can see how I solved it. Now, let me give you some few things in case you have the transportation model solved. There are some questions that you can get in an exam. Okay. In other words, you will not solve it in an exam, for example, situation. In an assignment, you may solve it. But in an exam, you won't solve it. Okay. And then you'll be asked a certain question. So here is a question. You were told that your mathematical model was solved using solver. And part of the output is shown in the graph below. Using the graph below, using the result, what is the optimal solution to the wheat problem? And you have to draw it first. What is the optimal solution? I wish there was time so that I can show you how to work this thing, how to actually do it in Excel. But like I said, the information is there. So when you go through the slide, you will learn how to do it. So this is the workings in the Excel, and this is the solution in the Excel. Look at the results. Remember that the information in the middle here are the results. The red information were 0, 0. Let me show you where they were 0, 0. Okay, so you can see here, they were 0, 0, 0, 0, 0, 0. Those were the decision variables. Okay. And then the amount that were actually shift are zeros. The amounts that were the cost is also not known. It was also 0. So these were the decision variables, and they were 0. But when you solved it, this is what you got eventually. So you can see that the decision variables are now having numbers. So for example, if you see 25 here, 25 here is referring to, it means that 25 tons of wheat were transported from Kansas City to Chicago. That's what it means. The Kansas cities are the elevators, the Chicago, Cincinnati, and St. Louis are the mills. So 25 tons of wheat was found eventually. That's what happened. Nothing was transported from Kansas City to St. Louis. So when you are asked what are the optimal solutions, the optimal solutions are these numbers. And you don't have to talk about the zeros, by the way. Just talk about the ones that are not zeros. So if I were to ask you, what is the optimal solution? The optimal solution are: 1, transport 25 tons from Kansas City to Chicago, 125 tons from Kansas City to Cincinnati, 175 tons from Omaha to Cincinnati, 175 tons from DM to Chicago, and 100 tons from DM to St. Louis. That's it. So you look at the numbers, you pick the numbers, the numbers will tell you. Don't mention 0 tons from Omaha to Chicago. There's no need to mention 0 tons. Because if it's not 0, it means it's not necessary. That's the first one. The second question is use your solution to find the optimal, the minimized cost, the minimum cost. How do you get the minimum cost? You can see that it is 4525 here. But how do you get it? Please, you will not see the 4525 there. It won't be there. So how do you get it? This is how you get it. Go to the objective function. Go to the objective function. Look at the numbers and then the decision variables. The decision 1, x13, sorry, x14. X14 is from Kansas City to Chicago. So the X1A or X14 will be 25. So it will be 6 times 25. The next one, which is X8, X1B, that one is 0, so you don't even look at it. So you are picking those that have the numbers, multiplying them each by the cost, their respective cost, and then summing them. Multiply each by their respective cost, and then summing them. Let me show you how you did it, how you can easily do that. These are the answers. The first one that we did, these were the answers. So this is how you calculate the minimum. So you do the 6 times the 25 because 25 was there. 10 times 125. Why is it 10 times 125? Well, you can pick them even from here. But when you redraw the thing, you see it. Here, 25, 125. Okay, then you have 175, then 175, then 100. Okay. So you pick their respective cost values and multiply them, and that will give you 4,525. Okay, so first let me go to Joanna, then I'll come to Mark.
Yes, sir. Please. The redrawn one, I didn't see the direction of the arrows.
Don't worry. Okay. Even though they are not there, you will bring them there yourself. when you are doing it, bring them there. Okay. Next question. Yes, Mark. Oh, but that was the same thing you're going to ask, I'm sure. All right, okay. So that's it. Let's go to transshipment. Let's go to transshipment. How do you do a transshipment model? It's the same as a transportation model. The only difference is that this time you have something like this. You have a transshipment node. You still have things being supplied to a demand, but then you have a transshipment node or transshipment nodes. So you have intermediary nodes first before you get to the end. The best way to explain that to you is to continue the example. So let's go to the example. Do you remember we said earlier that wheat are kept in grain elevators in 3 cities? And you were told that the 3 cities were Kansas City, Omaha, and Des Moines. Remember that? Okay. But what we didn't tell you is what we are about to tell you. We didn't tell you that those 3 elevators got the wheat from the farms. And the farms were located in Nebraska and Colorado. So because the farms are in Nebraska and Colorado, before being transported to the Kansas City, Omaha, and DM, now Kansas City, Omaha, and DM becomes transshipment nodes. There are no longer supply nodes. They are rather transshipment nodes. And then Nebraska and Colorado becomes the supply nodes. Nothing changes. The only thing that will change now is this. Tell me the amount that are being sent from Nebraska and Colorado to the 3 cities. That was having the grain elevators. Okay. What was the amount? That's what I need. And then what was the cost? So Nebraska and Colorado, what were they having? Well, you were told that the amount of wheat harvested at the farms is 300 each. 300 each. Remember, they are now the suppliers. But the Kansas City, Omaha, and Demore, they are now transshipment nodes. What do I mean? Let me just give you a slide draw. So it means that now we have Nebraska here, we have Colorado there, but the 3 cities, which is Kansas City, Omaha, Demore, they are now transshipment nodes. And then we already know our supply. The supplies were Chicago, St. Louis, and Cincinnati. So this is how the thing is going to look like. And you're going to have an arc from Nebraska going to Kansas City, from Nebraska going to Omaha, from Nebraska going to Deer. And then from Colorado going to Kansas City, Colorado going to Omaha, Colorado going to Deer. Before you now have what we did before, okay, which is this one going to there, going to that. This one going to that, going to that. Going to this one, going to that, and then going to that. Finally, this one, that one. So you're going to have a situation where inside these elements, you're going to have 1, rather 2, then this is rather going to be 3, then 4, then 5, then 6, then 7, and then 8. Where this arc here is going to be X, 3, 6. Okay. And then from this to that is going to be X, 3, 8. So what it means is that the objective function is going to be simply plenty. Before they were 6, but they are now going to be what? So now they are going to be how many constraints? You can tell me. And therefore the number of Pareto.
8.
8 constraints now. And that means your decision variables is going to be plenty. It's not difficult. It's going to be plenty. So this drawing is what I've just done. The rest is you name it. And remember, here is going to be 300. Here is going to be 300. And we already know that. What's the value here? I think here was 100. Okay. And here was 200. I've forgotten the full name, but it's still going to be 600 on the left here, and then 600 on the right there. Same thing. So let me show you how the objective function is going to be. When there's a slight difference, I'll tell you. So you are told to define the decision variables. Again, the decision variable is going to be the same. But this time you're going to say from node to node. That makes it easier. So look at the drawing. The drawing is going to be just as I showed. And I told you that the objective function is simply going to be plenty. And it is going to be plenty because the arcs are going to be many. Oh, guys, you need to know the relationship between the arcs and the node. For example, I want you to assume that there are nothing here. If there's nothing, no transshipment node, and you have only from this one going here, and then coming here, and then coming here. And then the second one, you are going to have this one going here, and then coming there and coming there. How many arcs do we have? How many arcs? How many decision variables do we have? You have to count them. Who used an approach without counting them? You got 6. Did you get 6? Yeah. Yeah, you got 6. How did you get a 6? Okay, suppose you have 1, 2, 1, 2. How many decision variables do you get? Let me see. Okay, I'm getting this answer. I want you to find a formula as I show you. Now, suppose you have 1, 2, 3, 1, 2, 3. How many decision variables do you have? Are you finding an approach? Okay, suppose you have 4 here. Oh, sorry. You have 4 and 4. 4 and 3. How many decision variables do you have? Four and 3. Somebody is sitting there and says, this one. So someone says 12. Okay. So 12. So on the basis of this, let me clear all. Yeah. Now, looking at what is on your screen now. How many decision variables do you have? Looking at what's on your screen. Without counting, using that approach you were using, those of you using the mathematics, how many decision variables do you have? Are you using the approach? You have to use an approach. The answers are not coming like before. Before the coming was, now I'm getting 12, I'm getting 15, I'm getting 18. So let me give you the rule, okay? 18, count, and let me show you. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so you have 15 decision variables. Now, those of you who are using the mathematics, your mathematics work only when you have 2. Only when you have 2, like demand and supply, demand and supply, demand and supply. So if you have 7 and then 7 demand, 7 supply, is 7 times 7, 49. If you have 5 demand, 5 supply, 5 by 5, 25. Okay, but that is when you have supply and demand. Supply and demand. Now, suppose there was nothing. See, I was covering this. Suppose this left side, suppose the two circles here, far left circles, Nebraska and Colorado are not there. Then it becomes 3 by 3, which gives you what? 9. But once you bring this, and this is the key, once you bring this, it doesn't work that way. Once you have transshipment nodes, but there's a formula you can use to get it. You can get it. There's a formula. So the one who multiplied, so one of you did this. This is what one of you did. You did 2 times 3 times 3. That's what you did. But that is wrong. If you did that approach of multiplication, that is wrong. What should it have been? Exactly. Okay. The way it should have been is there must be a plus in between. So it shouldn't be 2 times 3 times 3, because this will give you 18. That is not correct. It should be 2 times 3 bracket plus the other one, 3 times 3. Okay, then you get the answer. So when you have a transshipment node, that is how it's supposed to be. 2 times 3, that will give you 6. 3 times 3, that will give you 9. Then 9 plus the 6, that's 15. Okay. So that is how you get a 15. But if it is just, demand and supply, when you multiply straight away, you will know the number of what? Decision variables. I'm sure you get it. If you don't get it, you can reason. But I'm sure you get it. Justice, your approach, you see, your approach of 2 plus 3 times 3 is guesswork, but it must be following a systematic move. It is a factorized. So the one in the middle, must multiply the 2 outside. The one in the middle must multiply the 2 outside so that you are able to get what? You are able to get a plus. So anytime you have this, the one in the middle, the 3 here is in the middle, and the 3 here is in the middle. So the 3 is an intersection. That intersection must multiply this or must multiply the one on the right, and then you add them. That's what it gives you. Transshipment. Anyway. So, in fact, in your multiple choice, in your IA midterm exams, you get some of these questions. That's what I do that. Now, what about a constraint? How would you write a constraint? Now, please watch it carefully. Regarding the constraint, it's very simple. Once again, you have 300 here, you have 300 there. So that would be the supply constraint. So the supply constraint, you look at these acts that are leaving it. Okay, 1, 2, 3. They are all leaving it. Okay, so obviously it's going to be x 13 plus x 14 plus x 15, okay, and then equal to 300. I've removed the negatives. Equal to 300. That is for node 1. Node 2 is similar. And I want to go and do for 6, 7, and 8. They will also be what? Similar. How? Let's take node 6. Suppose I'm doing node 6. How will it work? It will simply have to be x 36 plus x 46 plus s 56 equal to 200. That's how it to be. Okay. But then what happens to the transshipment node is the most important thing. Remember, the transshipment nodes, there's nothing there. So the way you write the transshipment node is unique. It's easiest, actually. How do you do that? So watch. Follow me here. Follow me. All you got to do is to count how many acts are entering it and how many acts are leaving it. So let's take number 3. How many acts are entering Kansas City? It's 2. 2. Which are the acts? Well, first of all, you have x 1, 3 plus what? X 2, 3. They are entering it. Then that should be equal to the acts that are leaving it. Which acts are leaving it? Well, check it carefully. This one is leaving. This one is leaving. This one is leaving. So you have x 36 is leaving it plus x 37 is leaving it plus x 38 is leaving it. So the constraint for that one is what I've just written. So the constraint for this node 3 is this one. It's simply saying that the acts entering it should be equal to the acts leaving it. Finished. At this stage, you can group like this by moving those ones on the right-hand side or to the left-hand side. And then you'll be left with 0. And that's it. The same thing will be for the Omaha. The same thing will be, look at the acts leaving it, acts entering it, acts leaving it. Acts entering it, acts leaving it. Who can walk me through that of Omaha? What will be the constraint for Omaha? Node 4. Who can walk me through? What will be the constraint for Omaha? Who can walk me through? Having understood what I just did for Kansas City, who can walk me through for Omaha? Omaha. I hope you can hear me. Okay, you got Alex. Yes, Alex.
All right, Doc. Yeah, Doc. So for the constraints would be x14 plus
x14.
Yes. Plus x24 equals x46 plus x47 plus x48.
Perfect. That's it. That's it. So there are 8 constraints here, and 3 of them are going to be like this. So finally, let me show you the complete constraints for this transshipment model. Look at it. Look at the complete constraints. Of course, I've moved the left-hand side, the right-hand side to the left-hand side. And so we have a model that looks like negative on the left-hand side. That is it. Any question? I'm sure you are all clear. Who is not clear? Yes, who is not clear? Okay, so now that is how you do this. Of course, you can put this in Excel, which I've done for you. Look at it. This is how it is. Look at it and then solve it. Now, suppose I solve your model, I can ask you questions. So look at some of the questions I've asked you. This is the solution to the model. Okay, that's the solution to the model. Once you have this solution, I can ask you multiple questions. So the first question is, what formula? Look at this. Your mathematical model was solved using solver and blah, 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 blah. Use it to answer the question that follows. The first question is, what formula was typed in cell I11? So let's go to I11. Look at the Excel. They look very complex, but you can manage it. So you have I, look at letter I. The letter I is here. Okay, let me see whether I can label them nicely. So you have I here. And the 11, you have to look at this section. Okay. 11 is this. That is 11. So we are talking about this box here. That is the total cost, actually, the total cost. So it's asking you what formula was typed. Okay. So if you have been following the formula thing, then you should be able to know how to get this formula thing. What formula was typed here? How do you get the formula? Guys, remember that this is a total cost, and the cost required that you have the following. You have the individual cost multiplying the decision variable. Okay, that's all you have. You have the individual cost multiplying the x's. So the x's, the decision variables are what you don't know. Okay, so the decision variables, you don't know them. So where are they? Well, you can see them from here. You can see, it says here, shipped from, okay, shipped from 1. So let's take, for example, the first one here. This cell, and I'm talking about cell B2 here. You are shipping from 1. 1 is Nebraska, so he has told you the name. Ship from Nebraska to Kansas City. Ship from Nebraska to Kansas City. And what was the amount that you were shipping there? And remember, we are talking about objective function. So Nebraska value, we don't know yet. Okay. So you're shipping from Nebraska to Kansas City, and this is Kansas City. That's a 2. The 2 is what I've circled. So, but the item you are shipping is this. I'm circling that with a different color. The item you are doing is this. And it is going to Kansas City. So this 0, this cell A2 is your amount, is your decision variable, is the arc. Okay, that A2 is the arc, is the ship from, is the arc. And normally we attach this unit cost to it. Then this second one is when you are shipping from Nebraska to Omaha, if you can check. And the item is the 0 here, but we are going to define that with cell. So this first one is cell A2. So, and you're going to multiply that by the coefficient, which is a C. So once again, if you check this, if you check your objective function here, you will know. So you see 16x13 and then 10x14. All right, 16x13, 10x14. That is what is here. So the question is, and this is a 10. So he's asking you that how do you now get the cost? Now, normally what you would have done is that you would take the 16 multiplied by this 0 here, or the item. Normally it's not 0 before. Normally it is something. Okay. And then you take the 10 multiplied by what is here. So you're going to take everything that is in A and multiply it by everything that is in F, and then you add them. Then one formula you can use for this is a sum product. So you can say that sum product, okay, you can bring equal to, you have to bring equal to first when you're writing, because you're talking about what formula will be there. Okay. So this is a little bit tricky, so some of you will have to just pay attention. Okay. So equal to sum product A, and A what? A2. If you look at this one here, it is A2. A2 all the way to A2, comma, all the way to the last one here is A11. Okay, A11. And then F2 all the way to F11. So that is what you've got to do. That will give you this total. Look, another way you can do is that you can just say A2 times F2, A3 times F3, A4 times F4, A5 times F5, A6 times S8. And then you can do that. But normally that can take long. So this is the one that you can use. Let me show you how you would normally write. So if you use sum product, you get the answer. So that's it. You write A2, okay, I say 11, but it continues actually. Okay. Continues all the way to the end. A2 all the way to A16 here, and then F2 all the way to F16. And again, they will follow this same formula. They will follow this whole information. And if you look at this information, 2 to 16 is 15. And we remember that we said that the decision variables are 15. So if you count this, they are supposed to be 15. So your naming should be up to 15. So if you look at A2 to 16, that is 15 because 1 is not included. And then you do for the F2 to 16. And when you use this sum product approach, you'll be able to know the formula that will be there. I just wanted to know that sometimes you will get some of these things in that way. So go and look at it. Okay, go and look at it and that will guide you. The next question is what formula were typed in cells I2 to I9? That's very simple. Look at it. I2. This is I2 all the way to I9. Okay. So that's what I've circled. What formula was that? Remember, that one was not known before. Okay. I2 to I9. Okay. So if you check I2, it is information for Nebraska, Colorado, Kansas City, Omaha, DM, Chicago, St. Louis, and Cincinnati. So you have the constraints. These are the constraints. If you can remember, these constraints, that's what you have them there. I'm just taking you back. Okay, and I need to shift this. So look at the constraint here. So this first constraint that you see here, this first one, it is Colorado and Nebraska. Okay. Then the transshipment ones are the ones in the middle. These ones. They are all 0, 0, 0, 0. How do you know that from here? We'll go to the formula and see. So if you go down here to the formula that they are writing, see those ones are 0, 0, 0, 0, 0. Let me just write that. Okay. These 0, 0s, these are the transshipment nodes. So what formula will you put there that will be able to capture it? Well, you can see the formula is from the decision variables. Now, there are two possibilities you can use for this. Let me give you the difficult one. Okay. This is the difficult one. Let me clear this. So the difficult one is you can use sum if minus all of this, and then you can copy all of that through I9. But look, if you think that these things sometimes, I've thought that sometimes these things might, but go and look through this, by the way. What you can do is go check the formula here. Ask yourself, what am I doing to get to this? So this information is what we are looking at. This information. You are multiplying the decision variables to get the 300. As for the 300 on the right-hand side, which is in the formula here, this right-hand side information, you are not going to bother to touch them. Okay. But what you are going to bother to touch is this. Check the formula again. It is adding the decision variables x13, x14, x15, adding them together. And why do you get that? If you go to the Excel, yeah, if you go down there, let me just go down to show you the Excel. Okay. The one that gave us this -3, which is for Nebraska. Okay. To get that, you are supposed to take this one. Let me circle it for you. To get this, you are supposed to take 1, 2, 3. Okay. So you are supposed to add this one, A2 plus A3. Let me see the rest. You're supposed to add A2 hold on, let me just quickly get. That's why it's always good to use the formula to guide you. Let me just go to the formula again. So the formula says x13, x14, x15. Okay. 1, 3, 1, 4, 1, 5. So that is from Nebraska to Chicago first. So Nebraska to Chicago. Nebraska to, so I just need to look for Nebraska to Chicago. Where is that? Where is that? Where's Chicago? Oh, Chicago is not in the list that I'm having. Ah, there you go. Chicago. Okay, so you have Nebraska, A2 to Chicago, which is A2 to Chicago, which is D. What name should I go to? Yes, G6. Okay, so A2, G6, and then you have A3. Hold on. A2, G6, A2, G7, A2, G8. Okay. But this is going to be long. Okay, this is going to be long. So one of the easier ways you can do is to use this. So if you look at this dollar, of course, I've explained the dollar sign. So you look at D2 all the way to D16, everything. Now, it's not supposed to include everything. That is why you have to do minus. Okay, and then those that is not supposed to include, you now take the minus and then you can now deal with it. Other than that, it's taken from cell 2 all the way to 16, okay, and cell J2 all the way to 16. And that's what I was trying to show here for the J. Okay. Otherwise, you have to do it one by one by using the formula to be able to get it. So these are some of the formulas you will get. The last one is optimal solution. As for optimal solution, when you go to the graph, you will notice the optimal solution right there. Okay. The optimal solution is obvious. Look at the graph here. Those that have numbers are the ones you're going to pick. So look at the ones here. 300 is a number, you're going to pick that. Okay. 300 is a number, you're going to pick that. 300 is a number, you're going to pick that. 200 is a number, you're going to pick that. 100 is a number, you're going to pick that. So these are the ones that have gotten values. Okay. So let's pick the thing. It is from Nebraska to DM. So that's the first one, the first 300, Nebraska to DM. Okay. Then Colorado to Omaha. Then Omaha to Cincinnati. Then DM to Chicago, 200. Then DM to St. Louis. Okay. So those are the ones that have got positive values, and those are the ones that becomes the optimal solution. So you write them here. Let me just show you that. So when you go through the slides, you notice that these are the ones. So transport 300 from Nebraska to DM, 300 from Colorado to Omaha, okay, and then 300 from Omaha to Cincinnati, 200 from Omaha, DM to Chicago, and then just as. And then regarding the optimal solution, the total cost. The total cost is just taking these numbers, these 300, this 200, this 300, and the previous two 300s, and multiplying them by their respective coefficients. When you do that, you see this 300 respective coefficients, 300, 300, 200, 100. And then when you multiply them by their respective coefficients, you are now going to get this. And that will give you a minimum cost of 12,400. Go through this with your colleagues. Go through this with your colleagues. It will help you to be able to get an understanding. This one, when you work it together with colleagues, you are able to get the understanding. We are left to the very last one for today, and that is assignment problem. It's the easiest. It's the easiest, and it is it's the easiest. Normally, it's so easy that you wonder why it is there. So let's go to the very last one for today. Assignment. So assignment is simple. You remember the Premier League match. Let's assume that we have a center referee. In every Premier League, okay, there are 20 teams. So a team will play a team. Let me see whether I can do some bit of drawing here. Okay, I did some drawings here. So there are two teams. This is team A and team B. Or let's say this is Man United, this is Chelsea. And you have one center referee. One. There is no more than one center referee. And the teams are 20. So how many center referees should we have? I'm come to introduce assignment problem. How many center referees should we have, in total for the teams? And I'm not talking about the side referees. I'm talking, type it there, I don't need it. So we need 10 center referees, yes. Because each of the 20 teams will play one another. So we need another one center referee. If these two teams, okay, this one is Liverpool against Man City, okay, then Arsenal is playing Aston Villa. Okay, they too will need one center referee. So every week, okay, if they are all playing on a Sunday, you have 10 center referees. So the question now is, I have 10 center referees. I'm going to send them across the country to go and play the football, watch over the football. But I have to send them in such a way that the distance each will travel will be short enough that the total distance will be minimized. So some of the referees are also living in different places. So you may have a referee that is living in Scotland, another is living in London, another is living in Liverpool, another is living. So which referee should go and handle which match so that I will minimize total cost or I will minimize total distance? The most important thing is this. Please take note. This is the most important thing. Is the fact that each constraint, each game, each constraint, each game, each team, each constraint game will have one center referee. And therefore, this will always be equal to 1. So let's take a typical example. You will understand it very soon. Okay, this one is the easiest. Okay. So let's take, so the total supply and the total demand are always equal to 1. That's a key point you should know about assignment problem. Total supply. So I'm not going to give you a number for the total supply, like total supply for this. No, total supply should be equal to 1. Sorry, supply should be equal to 1. Demand is equal to 1. Okay. The supply is equal to 1. Each supply is equal to 1. Each demand is equal to. You are supplying one referee, one center referee to the game. And you are also demanding, that stadium is demanding one center referee. So the key point is that you want to find an efficient assignment of people to the game, or of projects, or people to a salespersons to a territory, or you have a number of auditors. Okay, which auditor should go and audit the account of which company? And things like that. That's what this one actually does. But the best way is to give you an example. So let's take this quick example. This is an Atlantic Coast Conference game. It's a basket game. Even though I described a football game before, we are going to look at a basket game. And basket games are usually played at night. Okay. So the people in charge in the US, the conference office want to assign 4 teams of 4 officials to the 4 games. So the games are happening in the towns, but they want to assign it in such a way that it will minimize the total distance traveled by the officials. Let me show you the distance and you will understand. So the team of official A, so in the official A group, the team of officials are A. And this group of officials, they are going to official the game. The games are in Raleigh, Atlanta, Durham, Clemson. Guys, if you're going to follow me, I'm going to ask you a question. And based on your answer, you'll be able to know. But these are the distances. Officials A will have to travel 210 distance to get to Raleigh, 90 distance to get to Atlanta, 180 distance to get to Durham, 160 distance to get to Clemson. Which one will, which town will the officials A be sent to? Going by the minimum distance. Which game would officials A go to? Would they go to Raleigh or Atlanta or Durham or Clemson? And once you are giving the answers, they'll go to Atlanta. Okay, I agree with you. Officials B, where would they go to? Officials B, where would they go to? And remember, no, just looking on the table, you just tell me, where would they go to? Official B. They will go to where? Atlanta. Official C, where would they go to? Officials C, where would they go to? They will also go to Atlanta. Finally, officials D, where would they go to? D. Officials D, where would they go? They will also go to Atlanta. Okay. So now it appears that all the officials will go to Atlanta. So it means that no official is going to handle the game in Raleigh, Durham, and Clemson. That's not good. All the officials cannot go to Atlanta. And you know, if you don't take care, you will say that, okay, then among the Atlantas, among the Atlanta, which official must go to Atlanta properly? What would you have said? Which official of the Atlanta will go to Atlanta? And the temptation will be that the officials D, isn't it? The question is that you may be wrong. Now we have to assign them in such a way that those in Raleigh will get officials. Those in Durham will get officials. Those in Clemson will get officials. Even though it appears that all of them got to go to Atlanta. So how do you do the assignment? The first thing is to define the decision variables. How do you define it? It's simple. The decision variables, as we know, okay, is always defined as the number of officials from node I to node J. And here node I is referring to what? Okay, it's referring to the team of officials. And the node J is referring to what? The town. Okay, so let Xij be the coach I, or team of officials I, assigned to town J. Team of officials I assigned to town J, or coach I assigned to town J. So that's how you do it. Now, how do you draw the network? It's very simple. Okay. Remember, you have 4 teams of officials, or 4 official groups. And then you also have 4 towns. So you got to do the arrangement in such a way that you have 4 nodes going to 4 towns. So that means that you need to have this one going here, this one going there, this one going there, this one going there. Then the next one, okay, this one going here, this one going here, this one going here, this one going there. Then the next one, this one going here, this one going here, this one going. I'm just doing it fast, but I know you can do it. Okay. Then the final one, you have this one going there, this one going there, this one going there, this one going there. And then you name them. If we are to say this one is 1, this is 2, this is 3, this is 4, and this is 5, 6, 7, 8. Then you can agree with me that this one will be X1, 5, okay, and then the rest will follow just as we did. So the same thing as that. What do you think should be the total amount we write here? Okay. You know, normally we write some numbers here, okay, like 200, 300 for the transportation. What numbers do you think we should write there? What numbers do you think we should write there? I want to see whether one of you will crack it based on the earlier point. What numbers do you think we should write for this supply here? For this supply here, what number should we be writing here? And then what number should we be writing there? Just type it for me. What number should we be writing there? Because when you are able to tell me the number, it means you have been following all these well. What number? And now that your colleagues have written it, you can copy them. Copy what they've written. Exactly, it's 1. Okay. So the total number of officials being supplied is going to be 1. The total number of officials being demanded, or coach being demanded, is also going to be 1. Okay. So that's it. So when you write a constraint, you should write a constraint in such a way that it's all equal to 1, equal to 1, equal to 1, equal to 1. And all you have to do is to look at the acts leaving that constraint and the acts entering that constraint. That's all. Okay. So with that in mind, if we go to the next part of oh, this thing is frozen. Just a second. All right. I'm sure you can hear me, right? Oops. Okay. All right, so let's draw the network model. When you draw it, this is what you get. Okay, I'm sure many of you will get an idea when I was drawing it. So this is it. Okay, so you have coach A, coach B, coach C, coach D going to Raleigh, Atlanta, Durham, Clemson. Of course, the numbers that you've seen I have attached here are just the distances. And as for naming the decision variables, AR means it's from A going to Raleigh. B going to Raleigh is BR. C going to Raleigh is CR. And as you can see, all of them. So that is how you draw it. Very nicely drawn. Okay. Now let's go to the objective function. Are we minimizing or maximizing? We are minimizing the distance. So how do you write the objective function? The way you write objective function is you write the Z min equal to, then you take the axe, just the axe. But each arc has a distance, so you have to attach the distance to it. So the first one is going to be 210, and then XER plus, so I just took this one. I just took this one here. Then you go to the next one. The next one is, if you don't take care, you'll be lost, so always monitor. It's 90 XAA. Okay, so plus 90 XAA. Then plus, and then you do all of that. You do each one of them. You're going to have, 16 information of decision variable. That's what you're going to have right there. 16 different ones. I'm sure you can model this whole thing. Let me show you how the modeling is done. It's very, very simple. If you follow the modeling process, this is it. You are going to get, I made this maximize. It's supposed to be minimized. I think I made an error. So you're minimizing this whole distance. The constraint. Let's go to the lesson. This one is subject to the constraint. Who can guess the first constraint? Because if you can guess the first constraint, let's do the first constraint for A, and then somebody will do the constraint for Clemson for me. Who can walk me through the first constraint for A alone? Because if you can do A for me, you can do all the rest. Who can do A? A constraint. Look at the acts that are leaving A. Always look at the acts that are leaving A. Always look at the acts that are leaving. The first act leaving A is XAR. Rebecca is ready to walk me through. Okay, Rebecca, walk us through.
Okay, so it is XAR 210. 210.
Rebecca, that will be wrong. Remember, I told you that when you are writing this constraint, you don't add the cost or distances.
So X
and it's not about you giving me correct answer here now.
Okay.
Because you got it wrong. But it's about you understanding why you are now about to give me the correct answer.
Thank you.
Okay. So what will it be? Don't worry, if it is a lot, let someone guide you. Let me go to He-Man. Alex.
All right, Doc.
Yeah.
So it will be XAR plus XAA plus
XAA, yes.
Plus XAC equals 1.
Oh, there's one more that didn't come.
Okay.
XAD.
Then we should have XAD.
Okay. Before XAC equals to 1. That's correct. Who can give me, so that's a constraint he just gave, the A. Who can give me constraint for Clemson? Constraint for Clemson. Who can give me that? Afia Seljanfi. Yes, give me for Clemson.
I've been lost, but I'm going to try.
Okay.
So Clemson is going to be sorry, hold on. Clemson will be okay. So Clemson will be XDC plus XCC plus XBC plus XAC is equal to 1.
Okay.
Hey, the way you're smiling, I'm afraid you both.
No, you are right. The only thing is I'm smiling because I don't know why you didn't start with the AC and you ended it with it. It's AC, BC, CC, BC. They are all in this terrain here.
So please, I have a question.
Yes.
Okay. Before we started, we said either of them, no, let me rephrase. Before we started, we said.
Sorry, unmute yourself and talk. Unmute yourself. Click on mute and then talk.
Okay, hello.
Yeah, go ahead.
Okay. I'm using the referees, the example we used in the referees. Okay, so we said we had several of the referees. Either one could be sent to a PlayStation, a playground or not. So I wanted to ask.
I didn't say or not. I said only one person, only one team can be sent there.
Okay, only one thing can be sent there.
Yeah, there are 4 human beings. Let's say that there are 4 there are 4 referees, and there are 4 games. Only one referee can go to one game.
Okay, I wanted to ask, although we know that they are all equal to 1, but I just wanted to ask, is it possible, because we don't know the referee that will be sent, can it be less or equal to 1?
No, because this is not, this is an integer. And once you say that it is less than 1 at all, it's going to be 0.
All right, very well. Thank you.
Okay. So this is how it's supposed to be. And when you check it well, you are very right in the way you want to do it. So when you check it all, it's all going to be this, like this. And then you don't forget your non-negativity constraint. This is how all the constraints are going to be. If you solve this, that will give you the proper allocation. So I did it and I got this result, this final result. And you can see that the ones here are telling you. So you can see that this is the final value. So the final value says that this is the 1, this is the 1, this is the 1, this is the 1, 4. So what does that mean? What it means is that, please, what it means is that one person, Atlanta, okay, one coach should be sent to Atlanta. Okay, but from where? That is the most important thing. One coach should be sent to Atlanta, but from where? Well, you can see from here that 90, this is the coefficient of 90. So you know A should be sent to Atlanta. And if you look at B, B should be sent to Raleigh. If you look at C, C should be sent to Durham. And if you look at finally, D should be sent to Clemson. So everything has been well defined. Perfect. So if they ask you what are the decision variables, those that have final values of 1. Here are the answers. And on the basis of that, you can now calculate the total distance. As for the total distance, when you're calculating, okay, when you're calculating the total distance, what you're supposed to do. Anyway, what I said is what I've written here. If you should redraw it, you will see that this becomes a final answer. So if I want to know the total distance, I multiply 90 by 1, 100 by 1, 140 by 1, 120 by 1, and then add all together. And that will give me 450. Ladies and gentlemen, that brings us to the end of the entire caboodle. You're supposed to close earlier than this, isn't it? But hopefully you've been able to get a picture.